Okay, so our session is being recorded. We're in section 5.9 and bringing up the ebook. So you've learned a variety of techniques for finding antiderivatives. And they're very good techniques, and they're used a lot. But there are also many integrals where we cannot find an antiderivative. So like a definite integral, remember, a definite integral is the area underneath a curve, well, underneath, above the x-axis. Well, I want to say this, the definite integral is an area that's underneath a function, below a function, and above the x-axis. Okay, or I better probably to say between the function and the x-axis from limits a to b. That area could be positive or negative depending on whether the function is above or below the x-axis. So how do we handle things if we have a definite integral that we cannot get the antiderivative of? We can't get the antiderivative. We have to approximate the integral, and that's where this approximate integration comes in, section 5.9. Okay, all right, and I guess, you know, the author is always there, or one of his or her relatives, I should say. Okay, or maybe a professor. I just want to say I'm not exactly sure who is doing these videos, but you know, they're qualified people, right? All right, so there are two situations in which it's impossible to find the value of a definite integral. Okay, and I'm not going to get too technical, but what they've done here is they've shown you a couple of integrals where you cannot find an antiderivative. You can, and if you can't find the antiderivative of the integral, you cannot evaluate the integral exactly. Okay, so that's the one situation. The other situation comes when you have a function that's determined from a scientific experiment through instrument readings or collected data, and there may be no formula for the function. We'll look at one of those later. But we have to ask ourselves, how did we originally learn on how to approximate the area under the curve? Well, what we did, of course, was we took the area and we divided the area up. Well, we underneath the function, we inscribed rectangles, right? We inscribed rectangles and then added up the areas of each rectangle to approximate the area underneath the curve. Okay, so like for instance, and I'm going to go right to the picture here. They're showing you some ways to do this. So in figure 1, you have here what's called the left endpoint approximation. So what they have is they have a curve. Okay, they have a curve, a function here in blue, and they want to approximate the area under the curve. So they draw some rectangles, but how are they drawing these rectangles? Well, there are 4 rectangles. Okay, so there are 4 subintervals, 1 rectangle for each subinterval. The first subinterval goes from x sub 0 to x sub 1. But what determines the height of that rectangle? Would it be the function value at the left endpoint, x sub 0, or would it be the function value at the right endpoint, x sub 1? What determines the height of that first rectangle? Is it f of x sub 0, or is it f of x sub 1? X sub 0, very good, Shalom, and not Nell. X sub 0. Okay, and if we look at the second rectangle going from, on the second subinterval, going from x1 to x2, okay, what's determining the height of that? Is it f of x1 or f of x2? Okay, it would be, good, Tina, good, Xiong, x1. So what's happening is you're using, in each subinterval, it's the left endpoint that's determining the height of the rectangle. The first rectangle there would be the difference, the base would be the difference between x1 and x sub 0 times the height, which would be f of x sub 0. The second rectangle would be the difference between x2 and x1, that base difference, times the height, which is determined by the function value at x1, f of x1. So we call that a left endpoint approximation. Okay, left endpoint approximation, and this is in the formula 1 there. They're saying that the integral from a to b of f of x dx is approximated by this left endpoint approximation, L sub n, where n is the number of subintervals that you're using. Okay, are there any questions so far with figure 1a? All right, well, for figure 1b, they're using the right endpoint approximation. If you notice, each rectangle, the height of each rectangle there is determined by the value of the function at the right endpoint. So the first rectangle, the height is at f of x1. The second rectangle, the height is at f of x2. Okay, so that's called the right endpoint approximation. Now you'll notice that the approximation's not, it's an approximation. The area under the curve isn't exactly equal to r sub n, in this case r sub 4. It's an approximation. But is there a way we can make the approximation better? How can we make the approximation better? Does anybody have an idea? The left endpoint approximation, the right endpoint approximation. How can we improve those approximations? What might be a way to improve them? Well, you know, Tina and Sergio, the midpoint approximation could give a better estimate. What they're referring to, Tina and Sergio, is if you look at the C figure here, they're approximating the area under the curve using the midpoint approximation. So they have each subinterval, they're taking the midpoint of the subintervals, and that determines the height. So the first rectangle, the height of the first rectangle is the function evaluated at the midpoint. The second rectangle is the function evaluated at that second midpoint. Okay. And this is great. This is great. Can offhand all these approximations, would there be a way to get a better approximation? Like, we used 4 subintervals for each of these approximations. Is there a way to make the approximations better? That's right, Tina. That's right, Justice. We can increase the number of subintervals. Absolutely, we can do that. Okay, and you know, we have these general formulas. So the midpoint rule, m sub n, is equal to delta x. Delta x is the length of each subinterval. Each subinterval is going to have the same length. Okay, delta x times the sum of the function values evaluated at each midpoint. So the way you have to think of this is if you distribute the delta x through the parentheses here in this midpoint rule formula, you're going to have delta x times f of x1 bar plus delta x times f of x2 bar, and so forth. Well, delta x times f of x1 bar is the area of the first rectangle. Delta x times f of x2 bar is the area of the second rectangle. Okay, so you're just basically adding up. It's a nice way. It's an abbreviated way of adding up the sum of the areas of the rectangles. The delta x would be, of course, the subinterval. You take the difference between the highest and lowest value from b to a and divide by the number of subintervals. And then the midpoint, I think you know how to find the midpoint between two values. So this is nice. This is nice. But yet there's another way that we can approximate the area under a curve. We can inscribe trapezoids. Okay, and that's what they have here in figure 2, a trapezoidal approximation. So here again, you have 4 subintervals, and for each subinterval, you're constructing a trapezoid. Now we use trapezoids because we can find the area of a trapezoid. The area of a trapezoid, maybe it's been a while, it's going to be 1/2 times the base times 1/2 base times the sum of the two sides of the trapezoid. Okay, and that's what they have here. And so if you were to add up all the areas of the trapezoids, you would get this general formula here called the trapezoidal rule. All right, and that's another way to approximate the area of a trapezoid, to approximate the area underneath the curve. All right. So far, are there any questions? All right. Well, there's another way too to approximate the area underneath the curve. There's something called Simpson's rule. That's in figure 7. So what I did was that's kind of cool. I used the arrow over here to get to Simpson's rule. That's figure 7. Simpson's rule, what is done is you for each subinterval, you actually you find the midpoint of the subinterval, and then with those 3 points, the left endpoint, the midpoint, and the right endpoint of the subinterval, you can pass a parabola through the points on the curve corresponding to the left endpoint, the midpoint, and the right endpoint. You can pass a parabola through the 3 points on the curve, and you can find the equation of the parabola. It can be done. You can find the equation of the parabola, and parabolas usually approximate curves better than line segments. Okay, so the Simpson's rule is another way yet to. This is Simpson's rule, another way to approximate the area under a curve. So these are all approximation techniques to approximate definite integrals. Okay, and we're gonna apply them, but we should also understand that when we approximate the area under a curve, it's helpful if we had an idea of what the error is. What's the error of our approximation? And to this end, in section 5.9, you have for the midpoint trapezoidal and Simpson's rule, you have what are called error-bound formulas. Okay, you have what are called error-bound formulas. And the error-bound formulas are given. They're given in that section, and we won't have probably time to go over the error-bound formula completely, but we will on Thursday's class. Okay, but remember in Blackboard in the course content area for, let me just hold on here. Let me now stop sharing here on this. One moment. Okay, let me go back into the course content. So under integrals, if we click here on integrals, approximate integration section 5.9, and of course I don't have the lecture posted yet, but numerical integration formula, click on that, and that's the formula sheet. And this formula sheet I made up to include all the required formulas you would need to do section 5.9, and you can download that formula. So that being said, let's go ahead and look at a problem here from section 5.9. Are there any questions in general? All right, well, if there are no questions, let me bring up a section 5.9 question here. Okay, and I want to stop sharing on this and bring this up here. No, I don't want that. Hold on. We'll get it. Okay, so there's the formula sheet, but let me get to the example. Okay, take a moment to copy this example down. Okay, maybe another minute or two. Okay, so we're considering this integral. Okay, we're considering this integral here. And the integral, of course, I mean, that is, I mean, I think it's pretty clear, but I want to make sure. This is the integral, right? E to the power of 1 over x dx from 1 to 2. Now, I can tell you that this integral there's no antiderivative that I'm aware of for this integral. Okay, I think one time a student said, I think a student said, I'm going to try to find this antiderivative, and I think he spent like 4 hours, and he wasn't able to do it. He was looking to get a Nobel Prize, I guess. There's no antiderivative for this, so we have to use an approximation. What we're going to do is we're going to use the midpoint rule approximation for this integral. Okay, we're going to use the midpoint rule approximation. So to that end, let's go ahead and well, so of course now the midpoint rule approximation would be this one here. Okay, it would be that approximation right there. And of course, in order to use the approximation, we need to establish what our midpoints are going to be. So the integral goes from 1 to 2. So to start the solution off, I'm going to draw a line segment that goes from 1 to 2, and I'm going to break it up into 10 subintervals, because remember, we're looking for m sub 10. Now, in your homework for section 5.9, 10 intervals should be probably the maximum that you have to worry about, okay? Because, you know, we can ultimately use a computer to help us, but we want to work this out by hand, these problems, so that we understand the process. So what I've done is, well, first of all, I'm going to give you a chance to copy that down, and you notice from 1 to 1.1, I have right between 1 and 1.1 an x1 bar. What would x1 bar be, by the way, from 1 to 1.1? What, I don't have a number written for x1 bar, but what is x1 bar equal to? What value? That's right, Tina. So what's 1.1 plus 1 divided by 2? And I think you can probably just visually get it. It's got to be, it's 1.05. I mean, halfway between 1 and 1.1 is 1.05. You know, what's halfway between $1 and $1.10? It's $1.05, right? 1.05. Okay, so this is 1.05, and I'm not going to draw all the values in, but okay, what's halfway between 1 and 1.1 and 1.2? What's the midpoint there? Good. Good, Tina. 1.1.15 and so forth. Okay, so I'll let you copy this line segment down. Let me put these in a little bit more nice. I'm doing the best I can here. $1.05, 1.15, okay, and so forth. Okay, take a moment to copy that down. Wait, question? Yes, not now.
Okay. I was gonna say, where'd you get the 0.1, but I see the formula.
Okay.
Okay.
And in the problem, yeah, n sub 10 means you're going to have 10 subintervals. And since your integral went from, well, hold on here, 10 subintervals, and since your integral, the definite integral goes from 1 to 2, you know, I find it easiest just to, you know, I'm going to need to use all these midpoints, so I just find it easiest to get them this way. How many kind of like this visual way of doing it? Any be nice maybe if I got maybe one thumbs up. Okay, thank you, not known Tina, appreciate it. Adriana, thank you. All right, so now the definite integral is approximately, notice we have an approximation symbol, not an equals. That's not correct notation saying equals. The definite integral is approximated by m sub 10, the midpoint rule with 10 subintervals. And now I write out the formula. And then, of course, I'll put in the midpoints. I don't write them all because you get the idea, but showing the work. Sometimes in these watch it videos, which I think students find overall helpful, sometimes I understand they do leave out some detail, but that doesn't mean you can't fill in the detail, you know. I mean, usually the watch it videos, there's enough as a guide for you to understand if you're having trouble how to do the problem, but you can always fill in more details. Okay, just like I'm doing here. So far, are there any questions up to this this step here? Okay, good, good. Okay, well then naturally, we have to evaluate each of these function values. The function f of x, I mean, here's our function right here. This is f of x. F of x is equal to e to the 1 over x, right? So f of 1.05 would be e to the 1 over 1.05. F of 1.15 would be e to the 1 over 1 to the e to the power 1 over 1.15. F of 1.25 would be equal to e to the power, the fractional power 1 over 1.25. And what I'm doing is in this homework, I mean, you know, if there were too many of these questions asked, then, you know, we would want to use technology to help us. But I'm not asking too many questions because I want you to go through the process of working it out by hand. And what I'd like you to do is I'd like you to type this whole approximation in your calculator. Actually type it out. And I want to see if you get the answer that I get. Okay, so take a moment and do that. Let me know if you have any questions. Yes, it is painful to type in. I know. And mathematicians, you know, 200 years ago would have to compute every one of these values. They have to compute each one. But the computation is doable, but not easy, but it is doable. So if you've done it right, okay, if you've done it right, and I've done it before, I'm not lazy or anything, I've done this already on my own calculator. Incidentally, the subinterval delta x is 1/10, because I took 2 minus 1 and divided it by 10. That's obvious. But who got for their answer, their approximation, 2.019101885? Tina did. Okay, good. Rodrigo, Tyreek, excellent. Did anybody get something a little different? If Surfiel, the number is 2.019101885. That's correct. That's correct, Sergio. Excellent, Tobias. So, and so like in WebAssign, when you work on this homework, and it won't be due till next week. But when you, well, hold on here, one moment. Right. When you work on this homework, WebAssign is going to want you to have like accuracy to 6 or 7 decimals, and it's going to want you to go through this computation process. Okay, it's not going to want you to use a program or something. It's going to want you to do it this way and get the answer that you get doing it this way. But anyway, that's the approximation. So our integral is approximately the area that we're looking for is approximately 2.0191010. Sorry, the area is approximately 2.019101885. But approximately, okay, we're saying approximately, but how good is the approximation? We'd like to know how good this approximation is. So what we're going to do on Thursday is we will continue this problem and work on the portions of the problem where we want to estimate the error in the approximation, and then we want to see if the approximation is an underestimate or an overestimate. So we're going to continue this problem on Thursday. But are there any questions on this at all? All right, I'll stop the recording.